Yes, so we left off with carbohydrates, and we're going to start with carbohydrates and all the macromolecules, and then all of 4, and then if we get to 5, I don't know if we will or not, but basically wherever we end up by the end of next Monday, basically. Okay, so this is where we left off. Now remember, one of the things I wanted to mention, first of all, got a screen share here. There we go. All right. So one thing I wanted to mention is covering nuclear lamina, right? So and actually all these slides here, we didn't really get a chance to talk about these, but these are kind of cool, right? Because this guy right here, that's a scanning electron micrograph of the outside of a nucleus. So you can see clearly these nuclear pores here. So you don't just have a couple of them, you have quite a few, right? So there's a lot of traffic going in and out of the nucleus. And this one is a transmission electron micrograph. So here you can see you've got your cytoplasm out here, your nucleus in here, and then you can see this double membrane. So there's your inner membrane right there. Your outer membrane is right there. So you can see actually how they kind of track along. And then they kind of come together in this pore structure. So there's your little pore right there in the middle. And so you can kind of see that very nicely, very up close. A lot of good structural information there, right? So you can actually see what it looks like. And this is the reason why we actually have a lot of knowledge now on cell biology, because of this electron microscopy invention. The other thing I want to mention, though, is on the inside of the inner nuclear membrane, you see this little guy right here. That is a little structure that's on the inside of the inner membrane. It's called the nuclear lamina. And the nuclear lamina, so this is an actual SEM of the inside of the nuclear lamina. So you can see this kind of gauze-like structure. These are actually fibers, protein fibers. That are composed of laminin. This is an intermediate filament. So basically you have individual little proteins of laminin that basically kind of form this sort of long, sort of filamentous fiber-like structure. And then each of these little fibrous cables kind of crosshatch, and then they kind of create this little gauze-like inside, very similar to the way that casting material is just basically gauze, and it's kind of like dipped into the casting compound, and then it sets up really strong. And so what this basically does is it sits here on the inside of the inner membrane of the nuclear membrane of the nuclear envelope, and this basically provides shape and structure. Nucleus. So without the nuclear lamina, basically what happened to the nucleus, it would just deflate. It would just kind of collapse down, kind of like a tent, right? So you have the frame of the actual tent that holds the fabric up. If you didn't have that frame there, the tent would just basically sort of collapse down on you. That's exactly what happened to the nucleus. It would just basically collapse down, lose its shape. And so the nuclear lamina is basically what creates this sort of circular shape and maintains sort of the tent environment of the nucleus itself. That's, by the way, a really, really good example of how intermediate filaments actually work. If you recall, intermediate filaments are part of the cytoskeleton. Remember, we said the 4 different functional groupings. The last one was the cytoskeleton. One of those fibers, the middle-sized one, was the intermediate filaments. This is an example of how intermediate filaments work. They basically kind of create this sort of support structure, if you will, this kind of scaffold, so that the cell can kind of have a little bit of structural robustness to it. Okay, so the next one in our informational group, the ribosomes. So the ribosomes basically are factories, little protein factories that themselves make protein. All right, so proteins that are involved in making proteins. So you can see this is another one of those evolutionary chicken egg questions, right? One of those little circular situations that evolution runs into every now and then. And generally speaking, doesn't really have a good way out of exactly. But this is kind of like, it's kind of one of those little oxymoronic sorts of things. And there are, in the ribosome, you have 3 major areas. We'll talk a lot more about the details of the function of the ribosome, what the ribosome does in the last chapter of the semester when we talk about protein synthesis, the mechanism of protein synthesis. But basically, the ribosome is made up of a couple of things. So it's an RNA and protein complex. So actually, ribosomal RNA is a structural component of the ribosome itself, which is the reason why you have an aggregation of RNA, ribosomal RNA, in the nucleolus, right? So if a cell has a lot of nucleoli in it, that basically is evidence of a cell that's really working hard at making protein. So it's kind of doing its thing. It's kind of doing its job. And so it uses ribosomal RNA as a structural component of the ribosome, but then it will interpret the code that is housed on the mRNA. Remember, we talked a little bit about how RNA is kind of like a working copy of the master blueprint. Well, mRNA is actually the working copy of it. And so this has the actual information that you need in order to select the correct amino acids. And then you have transfer RNA, which kind of is a mechanistic type of an RNA that allows you to select the correct amino acid that is encoded on the mRNA. So you see basically 3 different types of RNA involved in the overall protein synthesis process. And that's kind of part of what we talk about, is the roles of each one of these in a little detail in that last chapter. Now, ribosomes are interesting, right? Because basically you need these in order to make protein. So if you're interested in making protein, you have to have ribosomes. But the nice thing about ribosomes is you can kind of strategically sort of place them around. So for instance, you can have these guys free and floating in the cytoplasm, which is one way to do that, right? Or you can actually tether these guys to internal membranes, like say, for instance, the nuclear membrane. So what does this do for you? So what this basically does for you is, let's imagine that you wanted to make a bunch of proteins whose job is largely located inside the nucleus. Well, it doesn't make a whole lot of sense to send your ribosome way out into the back 40 of the cell, way out in the cell membrane, to make this nuclear protein, and then to try to figure out some sort of way to get that protein back to the nucleus, right? So when you have a situation like a ribosome, what you can do is you can basically tether this ribosome to the nuclear membrane, and it can make its protein there. So when the protein is done being made, it's already there at the site. And so all it has to do is just get to work. It's already there, right? So you kind of don't have to worry about spending extra ingenuity to try to figure out how to transport this protein all over the place to its correct job site. It's already there, right? Same thing's also true for the cytoplasm. You have an enzyme that's active out in the cytoplasm, then just send a bunch of ribosomes out there to make that enzyme. So once it makes it, the enzyme's already there. And once it's made, it just has to get to work, right? It's already there in its location. That's working. It's like on the job, on the site training. Protein factories that make protein. So they're little complexes of protein, basically, that make other proteins, essentially. So this is kind of what a ribosome looks like. So you'll see that basically you have 2 different subunits. So you have a large subunit in the ribosome, you have a small subunit, and typically the ribosomal RNA is in the large subunit section. As kind of a little bit of a structural component of that large subunit. And this is basically what we'll be making protein. So that's your informational group, right? So 1 down, 3 to go. So the second one is the endomembrane system. And remember, the endomembrane system, according to our outline, this is the one that had that big old laundry list of organelles to it. And we're going to be focusing on a particular mechanism that sort of pulls a lot of these together, and that's the secretory pathway, right? So that's one of the things we're going to be looking at. So the endomembrane system is basically a series of membranes, a series of organelles that basically takes you from essentially the nucleus all the way out to the periphery of the cell. And the reason why it's called the endomembrane system is because it does this without ever having to cross a membrane. So a protein typically is made and released without having to cross a membrane, which is the reason why they call it the endomembrane system, inside the membrane. So you have different stopping points in this trajectory. So from the point of being made to being released, there's several stopping points that you have to go through. And obviously the first stop would be like the ribosome, right? You're making the protein, that's what ribosomes do. But this basically represents, and we mentioned this before, a really huge innovation. Eukaryotes. Bacteria don't have anything, they're not even anywhere close to this level of innovation. And this represents a really, really enormous leap forward in the productivity of the eukaryotic cells over prokaryotes. The first stopping point in the endomembrane system. And the prokaryotes don't have those. Correct. I mean, not even close, right? And so usually when we say no membrane bound organelles, we're usually talking about a lot about this. The system really kind of doubles down on a lot of those membrane bound organelles and pulls them all together in a singular process. Okay. So let's take a look at that. Let's start our first stopping point, right? It's going to be the rough endoplasmic reticulum. So the rough endoplasmic reticulum is basically, this is like a labyrinth. Of membranes around the nucleus. And the important thing about the endoplasmic reticulum is, remember, it comes in two varieties, right? Rough and smooth. The rough is so called because it's got a bunch of ribosomes that are actually embedded and tethered to it. Remember, we just got done talking about ribosomes being able to be free, floating in the cytoplasm, or tethered to internal membranes. Well, these guys here actually have ribosomes attached to the endoplasmic reticulum membranes, which is kind of gives them sort of a rough, stubbly appearance, which is the reason why they call it the rough ER. Now, what does the rough ER do? Well, first of all, since it's got a bunch of ribosomes attached to it, what it does for a living is the synthesis of proteins, right? But think about it, right? We just said that if you're tethered to a membrane, it usually means you're not just making any protein, you're generally making proteins that are associated with that particular membrane system, right? So what's associated with the rough ER? Well, really, it's basically there's a series of proteins that the ER will make and focus on. The first one is proteins that are to be secreted, that is to say, to be released outside the cell. That's one type of protein that the ER will make, and the ribosomes on the ER will be making those. So its destination is outside the cell. The other one is going to be lysosomal proteins, right? Remember we talked about lysosome. We said the lysosome is basically the garbage disposal of the cell. Well, there's enzymes in the lysosome that we'll talk about a little bit later, and these enzymes come from the rough ER. This is one of the things that it makes. It also will make membrane associated or membrane embedded proteins. So those are three different types of proteins that the ER will focus on. Now, there's a lot of proteins out there, right? There's a lot of enzymes out there. There's structural proteins out there. We just talked about intermediate filaments, right, which is made of a protein called laminin. There's a structural protein, right? So there's a lot of different types of proteins out there that could be made by a ribosome, but the ones that are associated with the ER are only focused on these three types: secreted proteins, lysosomal proteins, and embedded proteins that are in the membrane itself. And so those are their three foci. And that's what's coming off of the rough ER. We'll take a little bit of a deeper and deeper look at that as we kind of get deeper into the secretory pathway. Now, before we get to that next step in the secretory pathway, let's take a look at our other type of ER, and that's smooth ER. So smooth ER basically doesn't have any ribosomes, relatively speaking, right? So a lot fewer ribosomes, so basically not rough looking. which is why they call it smooth. It looks like smooth membrane. And it has several different functions. The first one is lipid synthesis. So this is basically our source of new lipids. So remember, there's a lot of organelles that we're going to be talking about. All those organelles are typically membrane bound. That means that they have a lipid membrane. And so those lipids are composed of exactly the structure we saw before, right? Phospholipids, phosphate head, lipid tails, that is fatty acid tails. So depending on what types of fatty acids you have, whether they're saturated or unsaturated, those are the different types of lipids that you can make. And so if you need to sort of refresh your lipids, or you need to change them out a little bit, or change your mix, all that lipid synthesis is happening in the smooth ER. So that's a source of new lipids that's coming and sort of scattered throughout the cell. Storage of calcium is another big one. For those of you going on to AMP2, you're going to be running into this in spades when you get to the muscle physiology chapter. This basically, when you're storing calcium inside your muscle cell, is a type of smooth endoplasmic reticulum. They call it sarcoplasmic reticulum. But basically, this is a reservoir of calcium. And calcium is important to muscles because it's the calcium that's inside this particular smooth ER that, when released, is the signal for muscles to contract. So calcium is actually the ionic signaler for your muscle contraction. If you don't have calcium, you don't have muscle contraction. And that's true for all of your muscles. And so that storage of calcium is a critical function that you see in just underlying muscular physiology. The other one is detoxification. So detoxification is basically a situation where you have enzymes that detoxify something that you eat, for instance, and it has to sort of defang this, has to metabolize these particular, toxins that you just ate or whatever into a less toxic substance. So it kind of defangs them. A good example is alcohol dehydrogenase. So when you drink alcohol, it's actually considered by your body a toxin. So what happens is when you drink it, it gets absorbed, goes to your liver, and then your liver has to metabolize everything you eat. It has to make dangerous things not so dangerous. It has to process everything that you eat. So if you drink a lot of alcohol, then your liver will basically use the enzymes that are embedded in your smooth ER to detoxify the alcohol that you drank. Okay. And so not only that, but it is an adaptive responsive system. So for instance, if I don't drink, then it doesn't take very long for me to get a buzz, right? Because you're not used to drinking. Your liver has very few enzymes, right? So it has very few enzymes in the smooth ER. So I can easily overwhelm those enzymes and basically feel an effect. But what happens if I start to drink chronically? What's going to happen is the liver is going to be like, okay, this is your daily drink. So I'm going to increase the number of enzymes I'm going to put in the smooth ER. And then eventually what's going to happen is the same dose that I took all the while that I'm not getting a buzz from it anymore, am I? So what do? I drink more, right? Get my buzz back. I'm happy. And then what happens? Your liver says, oh, okay, so we're upping the ante. So that means I'm going to put more enzymes in the smooth ER, right? And then eventually you're drinking more, but it's not doing the same thing for you. And then what do? You drink more. You can see how this is going to go, right? Pretty soon, you're going to get to the place where you can pretty much drink an entire industry's worth of alcohol and you're still standing up. Why? Because your liver smooth ER is basically full of detoxification enzymes because it's ready. You got a habit of this now, right? And so it's ready to detoxify that for you. As a matter of fact, that's basically what we call what we mean when we say that somebody can hold their liquor, right? What are we saying? That means they can drink a lot and still walk a straight line, right? That's because they've got a lot of enzymes in their smooth ER in the liver that's detoxifying all of that alcohol. That's basically a sign of somebody who is no stranger to drink, right? And that there's a fairly chronic habit there, right? One of my favorite examples of this visual is from a classic movie, Raiders of the Lost Ark. Great one. I don't know if you ever remember when Indiana comes back to, I don't know where she was, Nepal or whatever, to meet Marion, right? And where is she working? She's working in like a pub or something like that in like Nepal or whatever. And then Indiana Jones, the original Indiana Jones, Raiders of the Lost Ark, right? So she's basically having a drinking game with this giant Sherpa. And you know, you can see they've been at it for a while because the table is full of shot glasses turned upside down, right? And here's this little itty frail looking, you know, figure of a woman. And, you know, she downs it, turns it upside down, and the Sherpa's all like, and he takes his and puts his down, and he just like keeps going, and it's just, he's out, right? He's gone. The amazing thing about that isn't necessarily how much she drank, as much as what she does after that. If you watch that particular scene, she basically has a full-on argument with Indiana Jones because he's like a former lover that basically jilted her. And so she's not very happy with him. And she has a pretty coherent conversation with Indiana Jones. Memory's fine. She remembers exactly what he did. Even when the Nazis showed up, she knows what to do to hide the medallion from the Nazis. And so it's like very aware. So that is a woman who can hold her liquor, right? She is clearly a heavy drinker. Her liver is full of enzymes, right? That's a good example of that detoxification effect. So this also kind of gets us to the idea of the functionality of a particular cell. As a matter of fact, there's some cells where you can actually, you know, you may not know anything about them, but you can actually kind of get an idea of maybe what they do for a living just by looking at the ratio of ER smooth versus rough. So here's an example. Remember, first of all, that your rough ER is focused on proteins that are secreted, released outside the cell, lysosomals, or membrane embedded proteins, right? Well, think about it this way. What do you think a gland does? Produces stuff, right? What kind of stuff? And for the most part, all glands, especially in the endocrine system, that's what I'm thinking of, not like sebaceous glands and the skin and things like that, but they're producing hormones of one type or another, right? And so in order to produce that, what does that mean? That means they're making it inside, yes? And then what do they have to do with it? Yeah, release it to the outside world, right? So if I take a look at a gland cell, and I were to look at its rough ER to smooth ER ratio, do you think this ratio would be high or low? Really high, right? Because it has a lot of rough ER because it's making a lot of secreted protein. So it's going to be really, really high, right? Now, let's take a look at what we just looked at. The example made Marion, right? And let's take a look at a liver cell, especially the liver cell of Marion, who is no stranger to the drink, right? What do you think her ratio looks like, high or low? Really low, right? Because her smooth ER is going to be really, really big, right? Because she's drinking a lot of alcohol. So this is going to be a really low number. So you can tell that your cell is actively involved in one of these three activities, either synthesis, storage of calcium, or detoxification, if it has a really, really low ratio. If it has a really, really high ratio, then it's probably putting out a lot of these, right? That's its main job. It's not very common that you're going to see both. It usually is one or the other. Okay. So you can kind of analyze that sometimes just by looking at the ratio of that. So it's kind of what it looks like. So here you can see this is your rough ER. You can see that kind of studded appearance with all those little gold ribosomes attached to it. You can see the labyrinth-like effect of the rough ER. And then as it kind of oozes into the smooth ER, you can see the smooth ER is a little bit different, right? It's not quite as labyrinthine. It's a little more tubular in nature, kind of like vertical tubes. And then when you cut in cross section, it just kind of looks like little circles. So you can see this is an actual transmission electron micrograph. of the rough ER. So here's your rough ER here in the blue. You can see all those like little black dimples there. Those are all ribosomes on there. So like that little guy right there, that's a ribosome. Whoops. So like that's a ribosome, that's a ribosome, that's a ribosome. So you can see a lot of them are tethered to this. And then of course your smooth out here just looks like a bunch of bubbles because you're looking at the cross section, you're looking like down into the center of the smooth ER itself. And the other thing that is kind of worth noting is the connection of the smooth or the rough ER with the nucleus. So if you take a look at the nucleus, you have an inner membrane, so here's your nucleus, and you have an outer membrane. But the outer membrane is continuous with the rough ER. So this is basically what it looks like. So essentially what's going to happen is you're going to have an evagination of the outer membrane of the nuclear envelope. And then it basically falls flat on itself because it's so big. That creates kind of one flap of the ER. Then this is going to evaginate and create the same thing. So you can see how the labyrinth begins to form. So the fluid basically of the space in between the inner and the outer nuclear envelope is continuous with the lumen or the inside of the ER, the rough ER. So basically the term, you'll hear me say that term quite often, lumen equals the inside of something. So you can see how you can kind of create this labyrinth by just sort of evaginating and then making it so big that it just kind of falls flat on itself. And then you kind of just keep doing that, keep puckering and keep falling flat. Okay. So that's kind of a thing that we see. So the next thing then, the next stop in this pathway is the Golgi apparatus, right? But before we get there, I'm going to connect it, right? Because the idea here is, remember, these ribosomes are on the rough ER. But what happens is the ribosomes in the rough ER are going to make the protein, and it's going to basically thread into the inside of the lumen. So you're going to have these like little folded up pieces of crude protein at this point, not ready for distribution yet, right? Still pretty much a crude product. And then what's going to happen is it's going to fill what's called a vesicle that is basically a swelling of the rough ER on the end. And that swells to the point where it just basically pinches off. So once this actually pinches off, then it creates a transport vesicle. And it's going to be full of crude protein. So you still have work to do on this protein before it actually becomes functional. Okay. Now, where does this transport vesicle goes? It goes to the next organelle, the Golgi, which is next on our list. So the Golgi, similar to the rough ER, is basically a stack of membranes that are kind of interconnected to each other, but they're kind of flat. They kind of look like a short stack. They're like a little stack of pancakes. And there are going to be two different locations of the Golgi. There's going to be what's called the sys face and the trans face. One's like a loading dock or a receiving dock. The other one's like a shipping dock, where it kind of leaves the Golgi. So what is the Golgi's job? Well, number one is it will pack, distribute, and modify or synthesize molecules. That's what it does. So crude protein basically means that this protein is lacking ornamentation. So here's a good example. So let's say that the protein that we are making in the ER is like a glycoprotein, right? That's a membrane embedded version of a protein. But what a glycoprotein is basically a protein that has a carbohydrate ornamentation on it. It's like got a branch of carbohydrate on it. So the crude version will come to the Golgi in need of modification. And so what the Golgi will do then is it'll basically trim stuff off. So it'll be like, nope, you're not going to make it. You're not going to make it. And this one right here is not going to make it. So my final product here is going to be this. That's it. So I modified it and kind of made it functional. Now what I have to do is I have to sort it. So where are you going, right? This is kind of like the UPS functionality of the Golgi. So where are you going? I need a zip code. I need a destination. So I need to know where to put you, right? So just like you have at the carrier facility, you always have this idea of the sorting out of things, right? So it's like, where's the destination of this package? Well, this is going to, Denver, right? 80217. So that means we have to put all the packages heading to Denver in the same plane, truck, or whatever, so that they can all get distributed to the same place, right? So that is the shipping and the sorting component. And so ultimately then you have to sort of sort this out and do this. So you have a package that you receive at the sys space, and then you have the modified version of it leaving at the trans space. So sys means same, trans means opposite, right? So that's basically what you have with cis and trans faces. And so the cis face is going to be receiving these transport vesicles, and then the trans face will be exiting more vesicles, but these are the secondary vesicles. So let's take a look at what this looks like. So here's our Golgi. So you can see it looks very much like a flattened, stack of pancakes. This is a TEM of a real Golgi apparatus. So you can see these like little flattened system of membranes. Each one of these guys is going to be working on various pieces of proteins and things of that nature. So your cis face is over here. This is on your nuclear side. So on the same side of your nucleus, this is the docking, so the receiving dock. So you notice the transport vesicle, which had come from the rough ER, is now moving into the cis face of the Golgi. And what's going to happen is it's going to dock with the cis face. So just like soap bubbles, when they meet each other, they fuse together. When this transport vesicle touches the Golgi, it basically fuses and then it dumps its contents into the lumen of the Golgi, and there it'll start getting modified by the Golgi itself. Then what happens is the protein starts to treadmill from one stack to the other, and it gets progressively more modified until it becomes perfected. So like it's ready to go, it's ready to do its job now. And so once you get down to the trans face, so you notice your trans face over here, which is toward the plasma membrane, then what's going to happen is you're going to basically pinch off a vesicle. So you can see one forming right here. And as it pinches off, it's going to basically pop off. And then you're going to have a secretory vesicle full of finished protein. This is the stuff that's ready to be released. This is like you're on gland and you're making a protein hormone. This is hormone that's ready to be released to the outside of the body so that you can actually communicate with cells in the rest of the body to tell them what to do. Okay. So this is an important
So the cis face is just good and trans face is good.
correct. Yep. So that's like the receiving dock, and this is basically this is like the shipping dock over here. So where everything leaves. Okay. And so basically then what this does, what we've done at this particular point, once you've actually created the secretory vesicle, what we've done is we've basically successfully walked our way through the secretory pathway. Let's take a look at the secretory pathway. So here you can see you've got your ribosomes studded to your rough ER. They're busy making proteins. So you can see some of these proteins are secreted proteins. That's what these little green squiggles are here. But you notice also some of them are going to be membrane proteins. So these little triangles, these basically represent membrane proteins that are embedded in the membrane itself. So this is a membrane protein here embedded in the membrane itself, and these are going to be secreted proteins. So then when that vesicle pinches off, then what you got is a transport vesicle with crude secreted proteins. So it's not ready for release yet. It's got to be modified, right? And also membrane proteins that are also crude as well. And then when it docks to the cyst face, you can see that basically what's going to happen is it'll basically dock into this particular area, and then it'll go through the Golgi being modified. So these are more modified, and then eventually you get to the finished product and you get to the secretory vesicle. Now, here's one thing I want to do here, because here we see our secretory vesicle, which will then go to the plasma membrane. And when it touches the membrane, it'll basically fuse with it, and it'll dump its contents to the outside of the cell into the cytoplasm. At that, into the external portion of the cell. At that point, that's secretion. So anytime a cell releases something outside of itself, that is secretion. So that's basically what that's doing. So the one thing I do want to make mention though here is if we take a look at this this vesicle, and if we take a look, say for instance, at a vesicle that looks something like this. So let's imagine that we have a membrane embedded protein that looks something like that. So these are just proteins that are embedded into this vesicle. You're with maybe like a bunch of secreted proteins in there as well. When this basically goes up to the plasma membrane and fuses with it, what's going to happen is it's going to fuse with this membrane like this. All those secreted proteins will come out, but what's going to happen is those membrane proteins will then be faced outside the cell. So for instance, these membrane proteins out here were once on the inside of a vesicle that fused with the outer membrane. So this is basic. So what you're doing is you're basically creating proteins and you're trafficking them out to the outer membrane, either to stay out there in the outer membrane or proteins that are secreted that get released and then they get circulated throughout the body. Okay. That's the secretory pathway. And you can see why it's important, because mechanistically it pulls together a lot of these organelles in the endomembrane system. Okay. But what about lysosomes? So lysosomes, if you recall, are the garbage disposal of the cell. So they're digestive. What does it mean to be digestive? Exactly, right? They're hydrolytic proteins, they're hydrolytic enzymes. And they're going to be breaking down all of the macromolecules, right? Lipids, carbohydrates, nucleic acids, proteins, all of them, right? So hydrolytic enzymes are the ones who do hydrolysis. They chop those polymers up into monomers. That's what they do for a living. So your lysosomes are full of them, but where do they come from? They actually come from the rough ER, or the rough ER is making these lysosomal enzymes. So really, when you take a look at a lysosome, all it is instead of a secreted enzyme, it's going to have hydrolytic enzymes, right? This is the sorting component of your Golgi. So whenever it's sorting things out, it's saying, okay, this protein, is it going to be secreted? Then I'm going to move it into this membrane bubble, and I'm going to call this membrane bubble a secretory vesicle. Its destination is the membrane to fuse with it so it can dump its contents to the outside of the cell. This enzyme, oh, you're a hydrolytic enzyme, aren't you? So I'm going to put you over here with my other hydrolytic enzymes, and I'm going to put you in another bubble that's going to pinch off of me, but that one is not going to be released. That one's going to hang out in the cell. We're going to call that one the lysosome, right? You can imagine then how critical this function is, because the last thing you want to do is release your hydrolytic enzymes to the outside of the cell, right? What would happen if your cell released lysosomal enzymes like through the secretory pathway? Yeah, right. You basically digest yourself. That's not a good thing, right, to do. So that would be a bad thing. So still, all you do, basically the only difference between the secretory vesicle and the lysosome, there's no difference, right? They're both membrane bubbles. They both have proteins. The only difference is which proteins they have inside them.
So does better allows mean facilitate or means to like facilitate the breakdown?
Facilitate, yes, that's a good way to look at it. Yep. So you're facilitating the reaction, the hydrolysis reaction. They make it go, right? Because basically these macromolecules don't break down if an enzyme isn't there to make it happen, right? The hydrolysis is the one that breaks those bonds, forms, you know, the monomer from the polymer as it pops off. So it has to do all this work. So that's what the facilitation is a good alternative synonym for catalyze. Okay. So then ultimately what's going to happen is anybody who gets on the business end of a lysosome is going to be phagocytized, right? Which is a fancy word for cell eating. So phago means to eat, cyte is referring to the cell, and osis is the condition of. So it's the condition of cell eating. Basically, what happens here is if you fuse your lysosome with anything else, it's going to chop it up. It's going to devour. It's going to digest it. Okay, that's the reason why we said it's a garbage disposal of the cell. The things you want to destroy, the things you want to grind up into nothing, you toss them into a lysosome. By the way, this is also the way some cells eat, is through lysosomal activity. This is also the way that your white blood cells actually behave. So for instance, when your white blood cells are busy attacking pathogens like bacteria, they do that through this process, phagocytosis, which basically means they surround the pathogen. So they kind of have this kind of oozing like capacity. They kind of surround the pathogen and then they kind of engulf it. And then they stick a bunch of lysosomes on it and they basically devour and chop up that bacteria. So that's actually how they work. Okay. And so this is kind of what it looks like. So there's two different things that will happen here. Number one is, let's give it a happier name than garbage disposal, because nobody saves their garbage. It goes to disposal and it's gone, right? So that's how that works. But this is like, let's do recycling. How about that one, right? So this is like a recycling strategy. So like in us, right, in multicellular eukaryotes, our cells have shelf life. So they're organelles, right? I mean, they're not around forever. We make them, they do their job, and then they get worn out, right? And then once they get worn out, we have to do something with it because we can't just let them hang around. So we got to destroy them. Preferably, we got to reuse them. So it's just like an old battleship, right? We do the same thing with battleships. So we'll make a new fancy dancy battleship. We'll send it to war. It'll do several tours of duty, maybe several different conflicts. It'll be out there for a while doing a great job. And then eventually every good ship sunsets, right? And we get to the point where it's like, you know what, that's done a great job, but the old war horse has to go down because we have to replace it with new faster ships. It's antiquated, it's rusty, it's getting, it's a floating rust bucket. And so now we have to basically scrap it. Okay, but oftentimes what'll happen is you don't just scrap it, you will actually part it out. So you'll basically break it all down. You'll take all the parts that you can reuse and refashion and use it for other cases, right? You'll recycle the old ship and it'll live on in other ships and things like that. Or in what we do these days for conservation purposes, we'll sink it to try to create a reef, right? Because trust me, our reefs need help. And they're actually quite good actually at creating false reefs. So we do that a lot these days. But this is recycling, right? So basically what happens is we have to scrap it, we have to recycle it. So what happens? So let's imagine we got this old damaged, or just old, doesn't have to be damaged, organelle. In this case, it looks like a mitochondrion. And it's time for this one to go. We have to recycle this one and use its parts. So what happens? We basically fuse our lysosomes to it. Usually it's probably more than one at this point. If you're doing this, if you're heavily recycling, you probably are making lots of lysosomes. So the rough ER is probably busy making hydrolytic enzymes and your Golgi is busy sorting them into lysosomes. So you're more than likely going to have several different lysosomes that are probably fusing with this. And eventually what's going to happen is you're going to create this sort of big, giant sort of vacuole, if you will, or big, giant structure, membrane brown structure with a bunch of hydrolytic enzymes in it that are just chopping away and just devouring all the macromolecules, right? So it's tearing all the lipids apart, tearing all the DNA apart, tearing all the proteins apart, right? Tearing everything apart and kind of reducing ourselves back down to the monomers, right? So what comes out of this is basically our monomers. So we get our building materials back and we can use those then to go and build new proteins with, new DNA with, we can reuse all that stuff. Okay. So good use. It's done its job. We're going to take it, scrap it down, turn it into monomers, and we're going to reuse those monomers to build new organelles. Okay. That's recycling. Now this one is eating. Right. This is a situation that you oftentimes see in phagocytic organisms. This is oftentimes how single cells eat. So what do? So first of all, what they do is they locate some sort of a food particle on the outside of them. This guy is right here. And then what they do is they kind of suck it in a little bit, and they kind of create this like little bubble by kind of sucking in. It's kind of go like that, just kind of suck it all in. And then what's going to happen is this is going to get pulled into this little this kind of little forming vesicle. And when these shoulders touch, then it's going to pop off, just like one bubble kind of popping off of your bubble wand, right? We're blowing bubbles now, right? So and then what's going to happen is it's going to create this little vesicle that we call a food vesicle or food vacuole that has some sort of material in it that you want to eat. And of course, you fuse a lysosome to it. It's going to dump those hydrolytic enzymes in there. It's going to digest it all out. And then from this, you're going to get your monomers. And if you're a single cell organism, that's because you don't have a stomach, you don't have a gut the way we do, right? So as a single celled organism, your lysosome kind of is your stomach. That's how you eat. Okay, that's how you acquire your monomers, is by doing this process. That's the reason why it's called phagocytosis, cell eating, right? It's just the process of your cell eating its food. Okay. So there's a lot of other little bubbles that come off of the Golgi. You can imagine all the different proteins that are possible, right? I mean, the different types of proteins. We talked about lots of them, right? We talked about transport proteins. We talked about enzymatic proteins. We talked about the whole laundry list of different protein functions. You can imagine all of those are going through the Golgi at some point. And so there's probably a lot of possibility in just basically sorting these out into different little membrane bubbles. So all a microbody basically means is just various membrane bubbles. All of them basically the same, just like a secretory vesicle is the same as a lysosome. The only difference is what's inside them. Same thing's all true here. The only thing that's different from a microbody, from a secretory vesicle, from a lysosome is what's inside them. Okay. Now there is one. Some of them will have different types of enzymes in them, and you can imagine there's entire families and groups of different types of enzymes. The number of different types and varieties of enzymes is a bewildering group. So just that alone is enough to create an infinite number of little membrane bubbles with different enzymes and things like that in them. But ultimately, they're all basically encased in these little membrane bubbles. That's all they are. Microbodies, just a little membrane bubble, not unlike a secretory vesicle, just with just various proteins in it. One of these microbodies that we run into that kind of stands out from the crowd is what's called the peroxisome. So this basically is a membrane bubble full of enzymes that detoxify the oxygen byproducts, which tend to be very oxidative. And also oxidation of fatty acids. So this is basically the breakdown and use of fatty acids. Yeah.
That's like non-oxidative or very oxidative?
It's very oxidative. So these byproducts are very oxidative.
Okay.
Yeah. So when you take a look then at what this looks like, and there's a lot of different enzymes here, but one of, and a lot of times people don't realize this, right? So oxygen, the consumption of oxygen is quite toxic. It's actually extremely toxic. As a matter of fact, to an organism that doesn't generally make use of oxygen, oxygen to them is like cyanide is to us. It's incredibly poisonous to them. It would be incredibly poisonous to us as well, except we have enzymes to sort of protect us from the negative effects of oxygen. So you're probably wondering, well, what's the big deal about oxygen? Right? I thought oxygen was good, right? You breathe oxygen, you live, you don't, you die. So that means oxygen good. Not necessarily, right? Because when you go through metabolism, when you metabolize oxygen through cellular respiration in order to make energy, which is why you need oxygen, the byproducts that you spit off are incredibly aggressive. So what we mean by oxidative, these are some of the most oxidative molecules we know of. These guys, what this means is these guys are hungry for electrons. Typically speaking, what we see in these oxidative byproducts are things like free radicals and superoxides. Basically, these are molecules that have unpaired electrons. And so they will seek electrons from others. What makes them dangerous is that they don't care where they get it from. They will basically rip an electron off of your tissues. And that could cause a lot of damage to your tissues because all they care at the end of the day is getting theirs. Okay. And that can become very damaging to your tissues. If it happens to your DNA, it can create mutations, which can be life-threatening, could cause cancer. If it happens to your tissues, it can create a lot of tissue dysfunction. And so generally speaking, you do not want a lot of free radicals and a lot of superoxides roaming recklessly about your physiology because they're going to do a lot of global harm. And considering how much oxygen you are consuming to maintain this very large multicellular body of yours, that means you are generating enormous amounts of these very oxidative byproducts. So it would not take very long at all for these oxidative byproducts left unchecked to create complete, absolute havoc and pandemonium physiologically on your tissues. It wouldn't take long at all. So what do we do then? Because it would be toxic, right? So if we didn't have these enzymes, by the way, like I said, it would be as toxic to us as cyanide. We'd die very quickly. Okay. So how do we get rid of these? Well, we have enzymes packed into the peroxisomes whose job it is to defang these very oxidative molecules. Okay. So has anybody ever heard of antioxidants? Right, it's a big dietary thing, right? A big nutritional thing. A lot, you go eat your blueberries. That's why, because you have a lot of antioxidants in there, right? Well, what are those? Well, what an antioxidant is a molecule that acts like a shield, right? So when this free radical comes for your tissues, instead of it ripping stuff away from your tissues, the antioxidant that you ate from your blueberries basically says, no, don't hurt my tissues, take me instead, right? So it kind of throws itself in front of the bullet, and then it gets, and nobody cares about that, right? The antioxidant just gets excreted out as waste, but it saves your tissue. This is one of the reasons why there's always a big pitch to say, try to eat foods that are rich in antioxidants. It'll help to reduce your cancer risk. Why? Because you're reducing the amount of damage that you're doing to your tissues. And therefore, you're going to be less likely to get mutations in your DNA, which if you don't get any mutations in your DNA, you're never going to get cancer. And so we'll talk more about cancer in chapter 10, which is the chapter after chapter 5, right? So that's what antioxidants do, but you also have these enzymes that do the same thing. So here's a good example, right? So we have hydrogen peroxide, which is H2O2, which is very oxidative, very dangerous. But what we have is an enzyme called catalase that hangs out in peroxisomes. And all catalase does, it's very fast acting actually, is it'll take peroxide and it'll turn it into water, harmless, and elemental oxygen, which is also harmless. Remember, it's not oxygen that's harmless or that's harmful to us. It's the byproducts of oxygen that get us. The elemental oxygen is fine. We're okay with that. So basically what happens is you have enzymes similar to catalase. There's other types of enzymes too, sulfur oxide dismutase. So, or superoxide dismutase. So you basically, an enzyme whose job it is to defang superoxides, right? So you have a lot of different types of proteins, and they all have one thing in common. They defang these oxidative byproducts. And we pack all those into our peroxisomes. And so that's what distinguishes a peroxisome from anything else. It's a membrane bubble, just like a lot of the other microbodies, but in this case, they're packing enzymes that defang these oxygen byproducts. Okay, so now let's take a look at the non-membrane organelles, right? So ribosomes obviously is a non-membrane organelle. This is something that's very specific to eukaryotes. And basically what we're going to do is we're going to take a look at what we just kind of came off of. So remember, we talked a little bit about lysosomes. And lysosomes have the ability to break stuff down. So they can defang and do sort of break down proteins and things of that nature. And you have a lot of hydrolytic enzymes that can sort of do digesting of proteins themselves, right? So here's the thing though, with eukaryotes, the amount of protein that you have, called the proteome, right? The entire universe of proteins in your cell is so big, and managing this is so important that you don't just leave it to one mechanism, hydrolytic enzymes. You actually have another one, which is specific in this case to proteins. So you have a separate protein grinder. And the reason why you have this is basically a big kind of a protein complex. Again, another one of those little chicken egg things in evolution, right? So you have a protein complex that digests proteins. So another chicken kind of egg thing, right? So the protein digester digesting itself, kind of an idea, but it doesn't digest itself, right? Basically what this does is proteolytic. So proteo refers to protein, lytic, lysis, right? The lytic cycle means cut. This is a protein cutter. That's what that means. Protein cutting activity. So what does it focus on? Well, it'll go after misfolded proteins. Remember our chaperone talk? Sort of. Or the chaperones, the ones that folded the proteins up. It was their job to sort of fold up the proteins. And what happens if they can't fold the proteins up? Well, guess what? That misfolded protein, it's got to go, doesn't it? So where does it go? What do you do? Stick it in a lysosome? Well, you could, right? But if you have a lot of misfolded protein, is that a good idea? Your lysosomes have a lot of other things to do, don't they? They can't just mop up bad protein. So you target your misfolded proteins into your proteasome. If your protein is damaged for some reason, or it's like been fractured, right? You send it to the proteasome. Or even if you just don't need it, right? You just basically need to reduce the levels. Send to the proteasome. And this is basically, this is an important one, right? Because this one here, this one is suggesting more like a protein regulation concept. Think about this. You don't just want to make protein, right? You want to regulate how you make it. You make a certain amount at certain times for certain purposes. Once that purpose is met, then guess what? Get rid of the protein. You don't need it any longer, right? So you have this dual purpose of I need to make a lot of protein at certain times in certain circumstances. So I need to have the ability to make it. But then when those circumstances change and I no longer need it, then I need to basically reduce those protein levels and go back to normal, right? So that's exactly what you do with the proteasome. So when you're talking about reducing or proteins that are no longer needed, this is a protein that may be fine. It may not be misfolded, it may not be damaged, it works just fine, but the circumstances have changed. The reason you originally made it has already been satisfied. You don't need the protein anymore. So now what you need to do, instead of having the protein sticking around doing nothing, that's a bad idea, right? You basically bring it all back down to original levels, right? Just like it's kind of like a crisis mode, right? Right. If you're dealing with a crisis, you want to be able to ramp yourself up into crisis mode so that you can have the awareness and the sensibility to deal with your crisis, right? To kind of stress yourself up. But once the crisis passes, guess what? You have to come back down again, right? To normal levels. It's not healthy to work at crisis levels all the time. It creates anxiety. So that's what you're doing here. You're managing the natural fluctuations of protein amounts in the cell, in the proteome. And the way you do this basically is you have a protein and let's say it's damaged or misfolded or whatever. But basically what's going to happen is you tag it with a molecule called ubiquitin, UB. And there's an enzyme called a ubiquitinase that actually does this. And when you tag it with ubiquitin, it's like the death tag. You've been marked for destruction. And so once you've been ubiquitinated, then what's going to happen is you're going to thread this protein into the grinder, this proteasome. And what's going to happen is this is basically going to grind this protein up and out comes your amino acids. And guess what you can do with that? You can send that back to protein synthesis. Go make some new proteins, ones that you need now, right? Because your circumstances have changed. So this allows you to continuously monitor and maintain and regulate your protein complement so that you only have what you need to fit your response. And the second you don't need that, scrap it, reuse it because your needs have changed. So now you need a different protein. So let me get those amino acids back and I'm going to go ahead and make that protein now. Okay. So you can see if you followed your amino acids, you'd be able to follow a life cycle of cycling from just amino acid into a protein. It would be used and then it would go to the proteasome and it'd be an amino acid again. It would go to another protein. It would be used, it'd be ground up and it would keep cycling back and forth. So any given amino acid in its life could potentially be used by multiple or be members of multiple different proteins before it's all said and done. So that's your proteasome. So like I said, that's a protein complex. That's basically like a big protein meat grinder. That's basically what that is. Now let's take a look at the vacuoles. So the vacuoles, you have a couple of different types, right? So these are membrane-bound structures. Typically, we'll find these in plants, but you have different types of vacuoles. And so I don't have enough space on these slides, so I'm going to insert here. There's three major types of vacuoles. We've already seen one. Actually, we've already seen kind of two a little bit, right? But we want to sort of lay them out here. First of all, there's the big central vacuole. That's this guy right here, right? This is the one that's associated with plants, this big membrane-bound structure in the middle of a plant cell that kind of sets plants apart, right? The central vacuole is oftentimes going to be have different functions, but for the most part, it's going to be a lot of storage. So it's going to be storing water and pigments. And different types of molecules that you store in there, but a lot of water. As a matter of fact, for plants, this is going to be your water management system. We're not talking about clean water here. We're talking about the amount of water, right? For instance, remember when you guys were playing around with salt concentrations in your Elodea, where you took your little Elodea leaf and you added salt to it and you kind of saw it plasmalize, right? So and then if you were to do the opposite, if you put fresh water in there, then you would have got the opposite effect. But all that water intake and release is all being managed by this central vacuole. So that's what I mean by water management. So it's basically managing your water content. And that's a pretty big deal. The other one is also a water content manager. This is what's called your contractile vacuole. This one you don't see in plants, but this is going to be, this is basically going to be your water balance. And especially protists, especially paramecium. You use paramecium as the poster boy. So if you take a look at a paramecium, it looks something like this. A little feeding groove there. So that's kind of what it looks like. But this is going to be one of those protists. And remember, you guys had a slide for this in lab 6. I'm sure you guys know it well now, or not. But the idea with this one is, where does a paramecium normally live? Well, most protists are probably going to be in like a pond, maybe fresh water, right? So think about this for a second. Do you remember what the mantra of osmosis is? That's a good one. That's the diffusion from the water. Yes, right. But the kind of the little memory trigger we did was salt. Salt sucks. Bingo, right? So it's salt sucks. That's our mantra, right? Which basically means that the salty area has a sucking effect. Remember, that's what we did with the sucrose bags and all that. It's kind of sucked all the water into it. We saw the weight of the bag increase in the 25%. The idea there was that the solute was sucking the water in toward it, right? And the reason why the bag didn't blow up is because it was a nice sturdy dialysis bag. But what if you're just a little guy like this and all you have is a little membrane around you? That's what a protist is, a single-celled organism. What does the inside of this particular paramecium look like relative to the freshwater pond? Yeah, is there a salt differential here? Like, is there a disparity in where the salty area is? Or is there like a high salt area and a low salt area? Where would the salty area be? Inside, right? Because it's got all those molecules in there, the macromolecules and proteins and things like that. All those are solutes. They're all dissolved. So what does that mean water's going to want to do to this little guy? So which direction will water go? It'll go in, right? And what's going to happen to him? Yeah, it would be like, right? It would be like, and then what's going to happen eventually? Yeah, because he has no, he's just a cell membrane, right? So it's going to be like a water balloon. Of course, now if you're a paramecium and you blow up, guess what? You failed, didn't you? You didn't live long enough to reproduce. You basically got yourself blown up. Not good. So how do you deal with this, right? Obviously, if a paramecium is going to live in fresh water, it's got to have some sort of a water balance system, some sort of a strategy to avoid blowing up. What is that? It's the contractile vacuole. So if we take a look at a contractile vacuole, well, it's very similar to your bladder in the sense that it's distendable and it holds fluid. So a contractile vacuole is just kind of like little membrane bound structure. It's like a little bladder-like structure. And it's attached by these like little channel-like tentacles that sort of extend out into the body of the cell itself. And so what happens is when it's not full, when it's kind of, it looks like a little star. You can see like the little channels kind of permeating the cell. But then as water comes in, what's going to happen is it's going to go into these little channels and it's going to fill up this internal bladder. So eventually what's going to happen is it's going to look like this. And then once it fills up to a certain level, it contracts. That's otherwise contractile. And when it contracts, it basically squeezes the water and shoots it outside of the cell. And then it goes back to its empty state again, where it basically soaks in more water, fills itself up, and then it'll contract and squirt the water out. It's not unlike if you were to take a sponge and basically clean up a mess, let's say an overflowing toilet that is continuing to come, right? You stick the sponge there, what happens? The sponge will mop up some of the water, right? And then what do? You squeeze it to get rid of it. And then you have an empty sponge and you go take it back, right? And it fills up again. You squeeze to get rid of it. And you do that again and again and again. And if that process of you getting rid of the fluid is faster than it's coming in, guess what? You live. But if it's coming in faster than you can get rid of it, guess what? You die, right? This is basically like the, this is kind of like the bucket brigade effect, right? If you think about like the Titanic, there's a big hole in the boat, water's coming in, but if there's enough passengers on the boat with enough buckets throwing the Atlantic out of the boat and back into the Atlantic, if that was faster than the water coming in, they could have made it to New York. As it turns out, there was actually more than just a hole in the hull. There was actually a huge gash in like the third of the ship, made it impossible for that one to happen, right? So that basically made that one impossible. But that's essentially what paramecium do. What they do is they basically bail water just to the outside. So you just keep squirting it to the outside. Of course, it's coming in, and you just keep squirting it to the outside. So as long as you keep squirting it outside, and you don't let it build up inside of you, then basically you just kind of maintain your unified size.
There's little channels that lead to the outside, right?
Yeah, one of them has to lead to the outside so that you can get directional flow. And I think it's usually just one of them. Kind of like with your bladder, we have two inlets into the bladder, right, coming from the kidneys, the ureters, that basically drain the fluid into the bladder, but we only have one way out. So that when you contract your bladder, you close off the inlet so that you don't shoot fluid back up into your kidneys. That would be pretty painful, right? So you close off your inlets, but you only have one way out, the urethra. So that way the urine goes out the urethra.
So some of those offshoots are for sucking in and some of them.
Yeah, and there's probably going to be one, maybe two that are connected to the outside that are designed to be the exit. So when it contracts, it only has one way to go out. And then you close that one off, and then you kind of let the others open up so they can take in fluid, and then you do the same thing.
If we have to do a contractile vacuum, if we just do it like that, we should show it some and some.
If you show it like this, it's fine. I mean, because the overall gist of it, I mean, you don't have to like be super perfect, like physiologically perfect on it, as long as you get the idea that this is basically, bailing water essentially. And that's what it does for a living. And of course, the other one is the food vacuole or the food vesicle that we just saw. And this is going to be fused with a lysosome. So this is basically how you're eating, right? So if you are a single cell, like a paramecium, then you're going to be taking in that food into a food vacuole, and then you don't have a stomach, so you're going to be basically using your lysosome to digest these macromolecules. Okay, so next one, the energy related, right? So this is going to be our mitochondria and our chloroplasts. So when we take a look at our mitochondria, right, this is basically, we find this everywhere. So all types of eukaryotic cells and all different taxonomic breakdowns, lower taxa, higher taxa, it's all across the board. You see mitochondria everywhere. And so the reason why you see it everywhere is because their job is to make ATP, right? That's your energy currency. So you can see then that the idea of making ATP as your rechargeable battery is an idea, a strategy that was answered a long time ago by a lot of different organisms, right? And so when you take a look at the mitochondria itself, it actually has a very interesting and very specific structure. So it also has a dual membrane system. It's got an outer membrane, it's got an inner membrane space, and then it's got an inner membrane that is folded up into cristae. So these are basically folds that are used to increase surface area. So you have an outer membrane, you have an inner membrane space, but these are basically, this inner membrane is folded into these like little cristae, like this. So you can see roughly I get the same volume, but I get a lot of extra surface area. Okay. And then of course I get the matrix, which is the center of the mitochondria. Now the reason why this is important is because these areas have a division of labor. The outer membrane has a particular function to it. The inner membrane actually has a lot of enzymes embedded in it. That's the reason why you increase the surface area, and these are directly responsible for making ATP. So that's the reason why you want to increase that surface area, because the more of that you have in there, then the more ATP you're going to make, the more energy you're going to have. So it basically makes the mitochondria a huge ATP engine, right? So a massive ATP engine. And then, of course, the intermembrane space is also important when you organize the activities of cell respiration. So the cell respiration activities are actually organized between these three structures: inner, intermembrane space, and the matrix in particular. So these proteins are going to be embedded in that inner membrane that basically allows you to carry out metabolism. That is basically, this is a fancy way of saying making ATP. Remember, we already use ATP. Now we're recharging our battery. That's what we're doing with mitochondria. We're charging that cell battery. The other thing that is also curious about mitochondria is that they have their own DNA. What? Wait, stop. What does it mean to have your own DNA? If I see something, I see a cell and it's got its own DNA, what does that tell me about it? Yes. It does have a different set of instructions, which leads it to being a different single cell organism. Think about it. All living things have to have DNA, right? To the point where actually DNA is the leading definer of living things, right? I mean, after all, if you don't have a master blueprint, you don't have a structure. If there's not a plan, you don't exist. So if something has its own DNA, what does that seem to suggest?
But it's its own living organism.
Right, which is exactly what Hussein said, right? So the idea that it's got its own set of instructions, which is how we define a living thing. Is it alive? Well, it's not. Yeah, right. So I mean, technically, it's not alive by how we define alive, but it definitely has. That's a curiosity, isn't it? It's like, what is that, right? So that doesn't make any sense. None of the other organelles had their own DNA, did they? They were all reliant on nuclear DNA. Go ahead, Kate.
How do we define alive?
That's a good question. Has to answer all the big biological questions of life, right? And so that's one of the reasons why we say that mitochondria isn't alive, because it can't answer all the big biological questions of life, right? So if we were able to take mitochondria out of a cell and have it be able to live and function and answer all, then we would say it's alive. But it's really good at answering a couple of big biological questions of life. But the presence of DNA suggests that perhaps at one point it did, but it has long since given that up, and it no longer has that ability, right? It's kind of like us now. It's like most of us probably couldn't raise our own food, at least if we needed to survive, because we left that back a long time ago, right? Because we said we're going to give out to the groceries, we're going to lose that skill set, and so that's gone now, right? Now, is there evidence that we used to be able to do that? Sure, because we all kind of have a little bit of a knowledge of it, but we're likely not going to be very successful in actually trying to put that into practice, because we just don't have all of the experience that you need in order to get that to work out. We've got ideas left over from that era, but we don't have the practice to go with it. Similar idea, right? It suggests that at some point you were able to answer more questions than just energy, but you can't now, right? Because you're not going to be alive outside the cell. This is what it looks like. You can see here, you've got your folds of cristae in here, and you can see your little ribosomes are also in there, and you can see your inner membrane space, your outer membrane. This is an electron micrograph. This is a transmission electron micrograph. You can see nothing looks like a kidney bean with tiger stripes. It looks that's very distinguishable. But notice these little guys right here, right? Those are those, remember that I said there's a plasmid-like DNA in a bacterium? Well, these guys are plasmid-like, little circles of DNA in the DNA in the mitochondria. So it looks a lot like those bacterial plasmids that we saw. And we noticed that right off when we started actually taking a look at DNA structure. We noticed it's like, wow, the DNA in mitochondria looks very familiar to us, right? Because at this point we'd studied bacteria a lot. At this point, we've done a lot of bacterial genetics, so we were getting good at playing around with these plasmids. And we noticed that it's like, oh, this looks very plasmid-like. This is interesting, right? Put a little mental dog ear in that one as we go into chloroplast. Chloroplast is the other ones, right? So these guys are going to be in the plants, not in the animals. By the way, plants also have mitochondria. One of the most common beginning mistakes is to say, oh, animals have mitochondria, plants have chloroplast. No. Plants have chloroplast and mitochondria. They have both, right? So it's just animals only have mitochondria. They don't have chloroplasts, okay? Because plants need ATP too. So they have to have those mitochondria as well. And so what they're doing is photosynthesis. So that's chapter 8. So basically they're taking sunlight energy and they're turning that into chemical energy for all of us, not just for themselves, but it actually turns out to be for all of us as well. But they have a very similar kind of a structure. They got two membranes. They have an outer membrane and an inner membrane, but their inner membrane is organized a little bit differently. They're organized in these like little penny-like stacks of membranes called thylakoids, and they kind of stack on top of each other into what's called a granum for singular, grana for plural. So these are stacks of thylakoids, and each of these stacks of grana are actually connected together with these like little membranous bridges. So they're all interconnected with each other. And it's in these thylakoids then that you have actually the photosynthetic enzymes. So you can see same strategy, right? You're increasing surface area in order to maximize the number of photosynthetic enzymes that you've got embedded into these little thylakoid membranes. And guess what? As it turns out, they also have their own DNA. Curiouser and curiouser, says Alice in Wonderland. Right. So here's what a chloroplast looks like. So here you got your outer membrane, your inner membrane, and then you have your thylakoids. So here's a thylakoid here. You can see how they're all interconnected with each other, creating granum. And you can see like these little bridges that are connecting the different grana to each other. And this is an actual TEM of a chloroplast. So here you can see the little stacks of thylakoids there. There's another little one right there. There's a little one right there. There's a good sized one right there, but they're all interconnected to each other with these little membrane bridges that kind of interconnect each other. And then the fluid in between them is what's called the stroma. So just like the matrix was the fluid inside the mitochondria, the stroma is the fluid inside the chloroplast. You can see a lot of similar themes here, right? Slight differences in structure, but the themes are very similar. But let's go back to this idea of them having their own DNA. Basically, them having their own DNA kind of basically piqued our interest. And it led to an evolutionary concept, right? Because in evolutionary biology, we're always trying to like reconstruct how it all happened. And there's a lot of people working on like, well, how did the first molecules come together? And then there's a group, how the first cells come together, and then all these sorts of things, right? So there's people working on various sorts of these. And so you had a bunch of evolutionary biologists working on how the first cells, especially the first eukaryotic cells, came to be, because you're talking about a massive amount of complexity in all these organelles, right, relative to the prokaryotes. So the question is, how did you get there? How do you go from a prokaryote or like an archaea to this really massively complex eukaryote with all these organelles going on in there and all this sort of stuff happening, right? So there's always kind of a question mark about how it all came together. Now, we can't answer necessarily all of it, but certainly with respect to the mitochondria and the chloroplast, we maybe had a hypothesis to sort of explain how they might have come to be. And that leads us to our endosymbiosis there. So endo, inside, symbiosis means it's a mutual relationship. That's what, so this is inside. And a symbiotic relationship is a mutual one. That benefits both parties. So each party is getting something from this. And generally speaking, there's different relationships between dual parties like this, and sometimes they're good and sometimes they're negative. Parasitism, for instance, is one where it benefits one but not the other. It actually harms the other, the host, for instance. But in symbiosis, it's usually a good thing, right? A lichen, for instance, is an example of a symbiosis. And so here's the different ideas that they had. So originally, and remember, we're talking about, you kind of have to take this one with a little bit of faith, if you will, because we're talking about things that happened about 3 to 4 billion years ago. So we're talking about a long time ago, which is the reason why there's a lot of variations to this theme, right? Because it's impossible to know for sure. But there's like maybe a half dozen different versions of this because there's different sort of permutations to this. So here's one of the ideas. Originally, this is not the way it started out. Originally, the end of symbiosis theory said basically we had a eukaryotic cell that basically what they did was it engulfed, like phagocytosis style. It's going to eat this guy. What was a protobacterium that looked a lot like a mitochondria. So it engulfed it. Now remember, when it engulfs it, it has a single cell membrane at this particular point. And when it engulfed it, it basically sort of wrapped itself around it. And then once it came in, it looked like it had a dual membrane to it. So the engulfing idea seems to suggest where the double membrane system comes from. Then what happened was this guy essentially was so useful in making ATP that the ancient eukaryote decided, you know what, I'm not going to destroy you because you're more useful to me alive because you're making ATP for me. So why don't I protect you and you make me ATP? That's the symbiosis. That's the mutual relationship. And hence, of course, since it used to be an ancient bacteria, it had a little plasmid to it. And so it hung on to that plasmid. And then this basically has an engulfed version of that. So there's a lot of different versions of that. Obviously, a plant engulfed a protist or a bacterium that was photosynthetic, like a cyanobacterium. And that got your plant. The question is, where did the nucleus come from? Well, some think that this was an ancient archaean that just got incorporated into like one of these little membranous bubbles that came spontaneously for free. And that's kind of where the nucleus started. And then the endomembrane system was just an extension of that. And so there's a lot of different ideas, like unknown bacteria coming in. So you can see there's a lot of different versions. Nobody really knows for sure how it all came to be. That's why I said it's impossible to know, right? Because we're talking about billions of years ago. But it's kind of an intriguing idea. It's largely just modeling and a little yarn spinning at this point. It's just so far ago. So it could be that none of our models are right, that it came together some different way we haven't thought about yet. That's also a possibility, right? Like spontaneous generation, right? Sounds good, but none of them are actually right. Cytoskeleton is the next, that's the beginning of the fourth and the last. Okay, we'll do that on Wednesday.